Welcome to Chapter 22, Electrostatics, Conceptual Physics. Okay, we're going to be talking about, of course, electrical forces and charges, the conservation of charge, Coulomb's law, conductors, insulators, superconductors, charging, charge polarization, electric field potential, and energy storage. Now, electricity is a name given to a wide variety of electrical phenomena such as lightning, the spark when we walk across the carpet on a cold day and touch a faucet, what holds atoms and you together, and sticks your socks together when you pull them out of the dryer. Electrostatics involves electric charges, the forces between them, the aura that surrounds them, and their behavior in materials. There's a central rule for electricity. It says opposite charges attract and like charges repel. So for instance, if we have and charges come in two flavors, positive and negative. That's just names that actually Benjamin Franklin gave them a long time ago. So suppose you got two positively charged balls here. They'll try to get as far away from each other as possible because there's an electrical force between them. Similarly, if you have two negatively charged balls, they'll also try to repel each other, again, because likes repel. If instead you have a positive and a negative, they'll attract toward each other. So this basically occurs from the fact that matter actually has charges. Typically, matter is made out of protons, nucleus with protons and neutrons in it, and the protons have positive electrical charges. They will repel other positives, but they will attract negatives. The electrons surround the nucleus in an electron cloud, and these have negative electric charges. They will repel negatives, but they will attract positives. The neutrons are also in the nucleus. They have neutral electric charge. Now, there's some fundamental facts about atoms. Every atom is composed of a positively charged nucleus surrounded by a cloud of negatively charged electrons. Protons carry the positive charge. Neutrons, which are neutral, help hold the nucleus together via the strong force. Each of the electrons in any atom has the same quantity of negative charge and the same mass. You cannot tell electrons from each other. They're basically indistinguishable. They're all twins of each other. A neutral atom has an equal number of protons and electrons because it is a charge balance. And the magnitude of charge on the proton is the same as the magnitude of charge on the electron. So in order to achieve charge balance, you need to have the same number of electrons you have protons. That, by the way, is a fundamental fact of chemistry. Okay, protons and neutrons compose the nucleus. The protons are about 1,800 times more massive than the electron, but each one carries an amount of positive charge equal to and opposite to the negative charge of the electron. Neutrons have slightly more mass than the protons and have no net charge. Atoms usually have as many electrons as protons, so the atom will have zero net charge and is electrically neutral. And that's a good thing, too. Okay, ions. Positive ions, an atom might lose one or more electrons, and then we'll have too many protons for the number of electrons that it has, so we'll have a positive net charge. A negative ion is where an atom will gain one or more electrons, and they have too many electrons for the number of protons it has, so we'll have a negative net charge. Now, the electrons in the atom are typically, the innermost ones are attracted very strongly to the oppositely charged atomic nucleus because they're close. And we're going to find out there's a law called Coulomb's law. It's an inverse square law. It's like the gravitational law. So the closer you are to something, more strong the electric force is on you. So whenever you've got something close, charges are close together, the electrical forces between them get much stronger. The outermost electrons are attracted loosely and can be easily dislodged, relatively speaking. This is especially true in metals. Anything on the left side of the periodic table is a metal. Now, examples of this. Okay, when you rub a comb through your hair, the electrons transfer from your hair to your comb. Your hair has a deficiency of electrons and becomes positively charged. The comb has stolen the electrons off your hair and becomes negatively charged because it has too many electrons. When rubbing a glass rod with silk, the electrons will transfer from the rod onto the silk. The rod becomes positively charged because the silk has taken the electrons away from the rod. The silk will have an equal negative charge. When you brush your hair and scrape electrons from your hair, the charge of your hair is positive because the electrons have been stolen from the brush and have wound up on your hair. So your hair would have a negative charge. Now, conservation of charge. In any charging process, no electrons are created or destroyed. Electrons just get transferred from one material to another. This is actually a consequence of the conservation of mass energy. Electrons have mass, and mass is equivalent to energy via E equals mc squared, Einstein's laws. So you cannot create energy nor destroy energy, so you cannot create or destroy electrons. They just move around. Now, Coulomb's law is the relationship among electrical force, charge, and distance discovered by Charles Coulomb in the 18th century. It states that for a pair of charged objects that are much smaller than the distance between them, the force between them varies directly as the product of their charges and inversely as the square of the separation distance. Now, if this sounds familiar, it's because you've seen this sort of law in the past. Think back to gravity. Coulomb's law says if the charges are alike in sign, the force is repelling. If the charges are not alike, the force is attractive. In equation form, F equals K Q1 Q2 divided by D squared. K is a constant. It's a large constant, 9 times 10 to the 9 Newton meters squared per Coulomb squared. The unit of charge is the Coulomb. That's the K, the Q's. Those are the charges. And of course, we abbreviate the Coulomb as C. It is an inverse square law, very similar to Newton's law of gravity for masses. Remember G, M1, M2 divided by D squared? And it underlines the bonding forces between molecules. Now remember that the G was very small, 6.67 times 10 to the minus 11th. This K is much larger. That reflects the fact that electrical forces are extremely large versus gravitational forces. They're only large when you got large masses. According to Coulomb's law, a pair of particles that are placed twice as far apart will experience forces that are 1/4 as strong. And that's just like with gravity. It's an inverse square law. Double the distance, 1/4 the force. Quadruple the distance, 1/16 the force. Differences between gravitational and electrical forces are electrical forces may be either attractive or repulsive. Gravitational forces are only attractive. So far, we haven't discovered antimatter. I wish we would. It'd be sort of fun. Okay, now there's such a thing as charge polarization. And what happens then is sometimes an atom or molecule in which the charges are aligned with a slight excess of positive charge on one side or a slight excess of negative charge on the other, said to be charge polarized. So for instance, if you rub an inflated balloon on your hair and place the balloon on the wall, the balloon will stick to the wall. Why is this? Well, what happens, the balloon becomes negatively charged because it rubs electrons off your hair. And if you get to put this on the wall, these negative charges repel the electrons that are in the wall. So they move slightly further away. And the protons, the positive charges, pull slightly toward the balloon. But if you look at this overall, remember it's an inverse square law. So what happens here is these are attracted to this with a certain force. They are repelled from these with a much smaller force because these charges are further away from these than these are. So the attraction wins. And we can say that this has been charge polarized. Now, a conductor is a material in which one or more of the electrons in the outer shell of its atoms are not anchored to the nuclei of the particular atom, but are relatively free to wander in the material. All metals work this way. They have relatively loose electrons called delocalized electrons, and they can just wander from atom to atom very freely. There are other types of conductors, acids, salt, water, bases, molten salts. In these, the ions are free to move. Insulators are materials in which the electrons are tightly bound and belong to particular atoms and are not free to wander around among other atoms of material. And so they don't flow, they don't conduct electricity. Examples of these are rubber, glass, most plastics, dry air, distilled water. Now, water on the surface of the earth is not distilled. It has ions in it, usually dissolved salts, and those will conduct. Semiconductors are material that can be made behave sometimes as an insulator, sometimes as a conductor, depending on what kind of materials you mix it with. These fall in the middle range of electrical resistivity between insulators and conductors. And they're insulators when they're in their pure state. They're conductors when they have impurities. And we often engineer them by putting impurities in them to make them conduct in certain ways. Semiconductors can conduct when light shines on them. If you take a charged selenium plate, selenium is a semiconductor, and you expose it to a pattern of light, the charge will leak away only from the areas exposed to the light, leaving a picture of the light. When you buy a water pipe in a hardware store, the water is not included. When you buy a copper wire, the electrons are in the copper wire, and that makes copper wire a bargain. Superconductors are materials that will acquire zero resistance, almost infinite conductivity to the flow of charge. In a superconductor, once the electric current is established, the electrons will flow indefinitely. With no electrical resistance, the current will pass through the superconductor without losing any energy, so no heat loss occurs when the charges flow. These occur usually only at very low, near absolute zero temperature, and for very exotic, expensive materials that are hard to work with, unfortunately. Now, you can charge by friction and contact. And if you've ever stroked a cat's fur, combed your hair on a dry day, rubbed your shoes on a carpet, you've charged something up by friction and contact. What happens there is the electrons transfer from one material to another by touching and rubbing. You can also just do it by touching. When a negatively charged rod is placed in contact with a neutral object, some electrons are moved to the neutral object. Now, you can also charge by induction. If you bring a charged object near a conducting surface, the electrons are made to move in the surface material even without direct physical contact. So, for instance, you have a thunderstorm here. Thunderstorms build up charge within them. The positive charge winds up on the top of the cloud, and the negative charge winds up on the bottom. And when a thunderstorm comes near objects on the ground, it can induce an opposite charge in the objects on the ground. So in other words, these negative charges here put a force, an electrical force on all the electrons inside of near the ground here, and that forces the electrons down further into the earth and leaves a net positive charge here. And that, if you're standing right here, that's not a good thing. You don't want to get between this and that. Now, you can show this by considering two insulated spheres, A and B. Now, we have to insulate them, because otherwise, if we charge this up, they're conductors. And if this is not an insulated thing here, this is just going to wind up going right into the ground. Now, we set them up so they touch each other. So, in effect, they form a single uncharged conductor. When you bring a negatively charged rod near the sphere A, the electrons in the metal are free to move, so they move over to the other opposite side of sphere B as far away from the negative rod as possible. And this will continue until there's a balance, okay, between the influence of the rod and the repulsion in here. And this means the charge has been redistributed. Now, what you do is you keep this rod near A but not touching it, and then you move B far away. What will happen is then of course you can take the rod away. What will happen is you end up with a net positive charge on A and a net negative charge on B. Here's a typical atom. Okay, you have a positive charge in the center, that's the nucleus, and you have a cloud of electrons surrounding it. And you can actually influence this. If you bring a strong charge near this, it can actually cause a distortion. In this nice symmetrical distribution, you can end up changing that. So you can actually induce the atom to become electrically polarized. What happens here is if you bring a strong charge near this, it ends up distorting this. And this is what happens here. Okay, the charged rod is negative, and then what will happen is the positive part of the atom or molecule is tugged in the direction toward the rod. The negative part, which are the electrons, are pushed away from it. And this charge separation causes the atoms to become electrically polarized. And this also happens when you charge up a comb. Suppose you comb your hair on a dry day, and you rub electrons off the comb onto your hair. You bring the comb near some other small object, like little bits and pieces of paper or fuzz. The molecules in the paper or the fuzz become electrically polarized. And it always winds up so that the charge closest to the comb is opposite to the comb's charge. And of course, the repulsion and attraction is an inverse square law. So the attractive side will win. Okay, so the attraction will win over the repulsion here, because this is going to be much higher force than this will. So what happens then is the bits of paper will experience a net attraction, and they'll be attracted to the comb. And you've probably seen this on dry days. Comb your hair, and then you can put your comb near something, like a small piece of something, and it will be attracted. It will try to leap toward the comb. Now, that kind of thing also happens with balloons. You rub an inflated balloon on your hair, it becomes charged. The balloon steals electrons off your hair. It becomes negatively charged. If you place the balloon against the wall, it sticks. This is because the charge on the balloon will induce an opposite surface charge on the wall. These negative charges here drive the electrons in the wall further into the wall and tug on the positive charges in the wall. And the closeness wins. This charge separation is very tiny, but the closeness wins. So what happens is this always attracts. And then if you stick the balloon on the wall, it sticks. It stays there because opposites attract. When we talked about this before, this is a temporary polarization. This only lasts as long as there's some strong charge near this. The minute the charge just goes away, this disappears and it goes back to that. There are some molecules, water for is a prime example, they're electrically polarized in their normal state. And this is because the distribution of electric charge is not perfectly even. So in this case, this is the oxygen. The oxygen is highly electronegative. It steals the electrons away from the hydrogens. Okay, so you have a net negative charge here and a net positive charge here. This is called an electric dipole. Dipole stands for two poles, so negative and positive, that's your two poles. So water is called a polar substance. It gives water many of its unique properties. Remember, we talked about water having a very high specific heat because of the bonding between water molecules. We talked about ice being less dense than water because of the fact that ice will form this rigid six-sided structure with a lot of empty space in it. This is the reason. It also makes it possible to boil water and cook food in a microwave oven. Microwave energy is basically electromagnetic radiation, and it will interact with the charges in the water molecule, and it causes the water molecule to flip back and forth, rotate rapidly and flip back and forth and dance around in the food, and that causes friction, and that friction is what heats the food. Now, all charges have an electric field surrounding them. It's kind of an energetic aura. It actually is a disturbance in space. It alters space, and the electric field describes the electric force on a small positive test charge. And of course, remember, around a charged particle, any charge will obey an inverse square law. What we do is we take a small positive test charge. It's always small, it's always positive. There'll be a mutual force exerted on both charges because likes repel. And in this case, the electric field strength, we can actually measure that by literally measuring the force. We know the magnitude of the test charge. We measure the force and divide it by the magnitude of the test charge, we can get the electric field strength. The units on this, you probably guess, newtons per coulomb. The unit on force is newtons. The unit on charge is coulomb. Now, the electric field direction can also be determined by the direction of the force on the positive test charge. And remember, it's always a positive test charge. If you bring a positive charge near another positive charge, they're going to repel each other. So the force on a positive test charge is always going to be away from this positive charge. If you bring a positive charge near a negative charge, the force is attractive. So the force on the positive charge is going to be toward the negative charge. Then we can say the electric field from a positive charge goes away from the positive charge. So positive charges are sources of electric field. The force and the electric field for a negative charge goes toward the negative charge. So negative charges are sinks for electric field lines. So electric field lines go from positive charges to negative charges. On top of that, notice here, as we get closer to the positive charge, the force is greater. That is represented by the fact that these electric field lines are closer together. So anytime you see electric field lines bunched up close together, or there's a lot of them, the electric field is relatively strong. As you get further away, there's fewer of them per area, and that means the electric field is getting weaker. So remember, electric field lines begin on positive charges and on negative ones. Where they're bunched up and close together, the electric field is strong. Now, both Lilly and the spherical dome of this Van de Graaff generator are electrically charged. And they have the same sign of charge because they're in contact with each other. And these are conductors. You're a conductor too, whether you realize it or not. Now, notice her hair is all standing up on end. So that hair also has whatever sign this charge is. Say it's all negative. So that hair will also have a negative charge. And it's trying to get as far away from her as possible. So it's standing up on end. That's the only way it can get far away from her as possible. And that's what we call a hair-raising experience. That's why you feel that tingle. Okay, so 1 Newton per coulomb is 1 volt per meter. Exactly. And here's some electric fields. Now, at the surface of uranium nucleus, you've got a lot of protons squeezed into a tiny space. And believe it or not, as further size, protons are really strong. 3 times 10 to the 21 volts per meter. Within a hydrogen atom, just 1 proton. But you're still close to the proton. It's 5 times 10 to the 11th volts per meter. Air breaks down at 3 million volts per meter. So that means if you see an arc that is 1 meter long, an electric arc that's 1 meter long, that means that there's probably a potential difference between the ends of that arc of 3 million volts. So you see an arc that's 1 inch long, that means you've got 20,000 volts between that 2 ends of that arc. That's how much it takes to get the air to break down, because air is a good insulator. Unless you put too strong an electric field across it, then it breaks down, becomes a plasma, and starts to conduct. And that's what the arc is. Okay, near a charged comb, do you realize you can have 1,000 volts per meter? It's a pretty strong electric field. Fortunately, there aren't too many charges there, so it's not dangerous. The lower atmosphere is 100 volts per meter. That's normal. Inside the copper wire of a household circuit, only 1/100th of a volt per meter. Now, electrical potential, okay, there's such a thing, just as there was gravitational potential and gravitational potential energy, there's also electrical potential energy. It is the energy possessed by a charged particle due to its location in an electrical field. Work is required to push a charged particle against the electric field of a charged body, and therefore you can end up changing the electric potential energy. It works pretty much the same as gravitational potential energy. You have a block, you crank it up. Okay, it takes work to do that, to move this heavy weight, this heavy mass against the gravity field here. And then, of course, when you cut this wire here and let it go, it slams back down to the bottom here. So what happens is the potential energy is being transferred and changed into kinetic energy. Energy loves to do that. It loves to change form. Here you have a similar situation, but now you have a negative charge here and a positive charge here. And you had to do work to separate these charges. You had to push this charge uphill, sort of up the electrical hill, to separate these charges. And when you did that, you did work on this. You increased the potential energy of this situation. If you cut the string here, the positive charge is going to go slamming into the negative one and will convert that potential energy into kinetic energy. It's pretty much the same situation. Also here, you've got the spring. The spring has more mechanical potential energy when you compress it, because you had to do work on this. Force it to be compressed. Force through distance is work. Similarly, you have charges here. These are positive charges. And we have, of course, this one is positive charge, excuse me. And you have another positive charge. If you want to move that positive charge closer to this positive charge, if you have to force it to be there, you got to do work on it. So this means there is more electric potential energy here than there is here, because you've had to do work on this. So the energy per charge possessed by a charged particle due to its location is its voltage. That's called its electrical potential. This is the potential energy per charge. In equation form, it's the electrical potential energy divided by the amount of charge. And of course, that would be V equals EP over Q. Now, you may have noticed, you might have this PowerPoint, unfortunately, likes to mess with subscripts. And so please make sure you correct this if you're doing this off your notes, PDF slides of your notes. It may say EP. It's supposed to be E sub P here. So please make sure you correct that. Unfortunately, PowerPoint, every time I save this file, it does that. It's really annoying. But the electric potential voltage, the units of measurement is the volt. And you probably guessed this, right? 1 joule, that's energy, divided by 1 coulomb, that's charge. So it's energy divided by charge. So for instance, you have a charged object here, and you have 2 other charged objects. And of course, they're all positive, so they're like sign, they're going to repel each other. So if we put these in the same location, they will have the same potential. That's sort of like putting them at the same height in a gravity field. Very much like that. They all have the same potential. Height's very much like potential. But this one has twice the charge as this one does. So this one is going to have more electrical potential energy than this one does. The same reasoning applies to the masses. If they're at the same height, but one has twice the mass of the other, the one that has twice the mass will have twice the gravitational potential as the one that has the small mass. If there were 3 times the charge in the same location, you'd have 3 times the electrical potential energy, but the same electrical potential. And that's because 3EP divided by 3Q is still the same as EP over Q, and that's V. Electrical potential energy is measured in joules. Electrical potential, on the other hand, is measured in volts, which is a joule per coulomb. The units can tell you a lot. Okay, now, high voltage can occur at low electrical potential energy for a small amount of charge. And that's the situation here. Do you realize when you rub a balloon on your hair, you can build up a charge of thousands of volts on both your hair and the balloon? Fortunately, there isn't a whole lot of charge here. It isn't dangerous. You can also have high voltage and high electrical potential energy when you have lots of charge, and then you do have danger because of this high electrical potential energy. That's where the danger is when you've got lots of charge. Okay, now we can also store electrical energy in a common device called capacitor. If you have a cell phone and you're holding that in your hand, you're holding thousands of capacitors in your hand, little tiny electrical devices that are made just for storing electrical energy and charge. The simplest capacitor is a pair of conducting plates separated by a small distance, but not touching each other. This is called a parallel plate capacitor because the plates are parallel to each other. When the plates get connected to a charging device such as a battery, the electrons are transferred from one plate through the battery to the other plate. Here's some pictures of capacitors, by the way. Now, this will happen because a positive battery terminal will pull electrons from the capacitor plate connected to it, and these electrons are in fact pumped through the battery into the negative terminal to the opposite side plate of the capacitor, to the negative plate of the capacitor. The capacitor plates then have equal and opposite charges. The positive plate connected to the positive battery terminal, and the negative plate connected to the negative terminal. Now the process continue until the potential difference between the plates equals potential difference between the battery terminals. In other words, until the capacitor potential equals the battery potential. The greater the battery voltage and the larger and closer the plates are, the greater the charge that can be stored. The energy stored in a capacitor comes from the work required to charge it, so the battery had to do that work. And you can get that back, okay? If you discharge a charged capacitor, that can be a painful experience if you happen to be the conducting path. Now, if you happen to have an old-fashioned television around, you know, the kind that had the big tubes on it, come in a big square box, never reach into one of those. Do not mess with anything inside of one of those unless you know what you're doing. If you have an old-fashioned amplifier, you know, the ones you use on your stereo or something like that, if you look inside of that, please look and do not touch. You might see things that are big and round, sort of like look like soda pop cans, kind of that shape. Don't touch those things unless you know what you're doing. Even when the device is unplugged, they can store a charge for up to a week or more. If you get across the wrong part of those, you're going to get a shock that you will never forget. Now, this is a common laboratory device for producing high voltages and creating static electricity. We're not going to go over this much because we can't really demonstrate it in the class. Okay, now electrons hate each other. They repel each other. So they flee the inside of any charged conductor and hang around only on the outside. So here is a charged conductor inside a parallel plate capacitor. If you charge up the capacitor, there will be a very strong electric field in here. And notice there's no electric field inside this conductor right in here. That's because all the electrons wind up on the outside. They try to get as far away from each other as possible. And so the electric field inside any conductor is zero under electrostatic conditions. So where should you go in a thunderstorm? Inside a conductor. The easiest conductor to find is your car, provided it's a hardtop car. It has absolutely nothing to do with the rubber tires. Notice here, see the arc across that tire? Yeah, okay, that will not stop this. Okay, look at the size of this. Remember I told you it's 3 million volts per meter? That car is probably about 1.5 meters high. There's probably 2 meters here. So that might be 6 million volts. That little poultry tire is not going to stop 6 million volts. In fact, tires are actually made to be conductors. Modern tires have steel belted radials in them, and they have carbon in them, which makes them black. They're actually made to be conductors for safety reasons. So it has absolutely nothing to do with rubber tires. It has everything to do with the conductivity of the metal. The fact that electrons will hang around the outside of the conductor and will flow through the outside of the conductor just because they don't want to be close to each other. The metal object is called a Faraday cage. And notice this guy is perfectly safe inside of this Faraday cage. He's sitting on the seats. He's got his feet on the floor. He's touching the inside of the metal body. It's perfectly safe to touch the inside of the Faraday cage. But you don't want to get out of the Faraday cage. So if this ever happens to you, stay in your car. Don't get out of the car. And please don't let this happen to you. Okay, so any hollow metal object is a Faraday cage. Here's a modern car. And by the way, showing the same thing happening to this. And look at the distance here. Okay, that's probably at least 10 million volts there. Yeah, that tire is not going to do anything to save you from the 10 million volts. In fact, it's going to conduct it right to the ground. So here's a picture of a conducting object here, of a Faraday cage. And here, these little lines here are the electric fields. Notice they're perpendicular to the conductor at all points. Notice that there are none of these lines inside this conductor. They're all on the outside. That's because the electric field inside of this is zero. Now, when the electric field is zero, everything is at the same potential as everything else. Not necessarily zero potential. This whole thing is probably about 6 million volts, but the whole thing is the same potential. So this creates a shield from electric fields, and it's an equal potential surface. That's why this guy is safe. So inside a Faraday field, the E field is zero and everything is at the same potential. It is differences in potential that harm you. And since you're inside an equal potential surface, you're safe inside, but you must stay inside. Don't get out. This is used to shield sensitive electronics, such as you put metal cases on computers. And to keep electrical workers safe, they wear conducting suits when working on high tension lines. Downside to this is that cell phones and Wi-Fi, which depend upon electric fields to work, often do not work inside of well-shielded buildings. buildings are dead zones. Now, on campus, in our building, until we got little Wi-Fi repeaters all over the place, cell phones would never work inside the building, which was a nuisance. But this is the reason these buildings are great shelters from lightning, and this is the reason we look outside of our doors. All those rooms are tornado shelters. Part of the reason. Tornadoes are spawned by severe thunderstorms. So this building is very strong. Where are all the conductors in the building? Well, actually, the building is made out of concrete. Remember I mentioned that you put rebar inside of concrete to make it strong? Well, rebar is made out of steel. Steel is a good conductor. So concrete buildings, real heavy, strong concrete buildings, are often great shelter from lightnings, and they're also good shelter from tornadoes. And lightning and tornadoes often go together because tornadoes are spawned by severe thunderstorms. I hope this never happens to you. Have you ever experienced this during a thunderstorm? You're standing around outside and suddenly feel your hair standing on end. Well, this is the reason they tell you on the Weather Channel, when thunder roars, go indoors. You would not want to be in her shoes. Now, if you notice carefully, if you look very carefully on this picture, there's a very faint yellow light here. This is a plasma streamer. And this is the air breaking down, starting to ionize and become a plasma. Plasmas are a good conductor. Above her is a thundercloud that is driving this. There's a very strong electric field here. That's the reason her hair is standing on end. Okay, so cloud bottom is negatively charged. What happens? The negative charges are going to repel the negative charges in her and drive them further into the ground. The negative charges drain off of her and she becomes positively charged. And her hair also becomes positively charged, which is why it's standing on end. And meanwhile, an upward streamer is forming here. The air is breaking down and starting to become a plasma and starting to conduct. The next thing that can happen is the lightning bolt. So this is what happens. Now, notice if you look very carefully on this picture, this is a tree that got hit by the lightning. Notice that there's a faint upward plasma streamer at the top of the tree, just to the left of this main bolt. There was probably another one here that actually made the connection to the cloud. This one didn't quite make it. But this is where you don't want to be. Never stand under a tree. They're high objects and they can be a lightning attraction. Now, where should the person go to avoid a painful and perhaps fatal outcome? Get inside a sturdy building or a metal car, not a convertible, and definitely not a golf cart. A lot of electrical lightning deaths occur on the golf course. Never stand under a tree. Your golf cart is not a protection. When lightning roars, get indoors. Now, lightning safety. Stay away from high places, trees, metal poles, fences, and definitely stay away from water. Get inside a car or building. The plumbing and electrical wiring will act as shielding. Do not touch plumbing or wiring or things connected to them. Stay out of the shower, off the landline phones. You're perfectly okay on a cell phone. Contrary to popular belief, cell phones are perfectly safe inside. They're not connected to anything. If caught outside, do not lie down on the ground. A nearby strike can travel through the ground. That's called a ground current, and that often kills people. Go inside or get as low as possible. Now, you might have noticed this on top of some buildings. These little spikes sticking up. Here's a close-up picture of one of these. They actually have a wire that connects to ground. And what they do is, these are called lightning rods. They were invented by Benjamin Franklin. They're placed along their highest points, and what they do is bleed off charge and don't let it build up. And what they do is basically conduct the charge to ground, safely bleed it up before this builds up and makes the air break down. On top of that, even if lightning does strike these, hopefully these will conduct the charge to ground and away from the building, or it can do harm to the building and to people. The net charge of an atom equals 0 if the atom is electrically neutral. Atoms always try to be electrically neutral. If a neutral atom has 22 protons in a nucleus, the number of surrounding electrons is also equal to 22, because an atom with 22 protons in its nucleus with more or less than 22 electrons is an ion. The magnitude of charge on the proton is equal to the magnitude of charge on the electron, but opposite in sign. In order to become electrically neutral, atoms need to have the same number of electrons as they have protons. When we say charge is conserved, we mean that charge can neither be created nor destroyed. This is a consequence of the law of conservation of energy. A negative ion has more electrons than protons because the electrons carry the negative charge. According to Coulomb's law, the force between a pair of charged particles that are brought closer together will increase. It's an inverse square law. Just as gravity, the force of gravity increases between two masses that are brought closer together, works the same way. When a pair of charged particles are brought twice as close to each other, the force between them will become 4 times as strong, in accordance with an inverse square law. Unlike Newton's law of gravity, Coulomb's law involves repulsive as well as attractive forces, because so far we haven't discovered anti-gravity. Gee, I wish we would. That would be fun. When you scuff electrons off a rug with your shoes, you're taking the electrons from the rug to the shoes. That means your shoes have an excess amount of electrons on them. Electrons are negatively charged. So your shoes become negatively charged. The rug will become positively charged, and the magnitude of the charge on your shoes will equal the magnitude of charge on the rug, because electrons are neither created nor destroyed. They only get moved around. When a cloud that is negatively charged on its bottom and positively charged on its top moves over to the ground below will acquire a positive charge. When a negatively charged balloon is placed against a wooden door, the positive charges in the wall are attracted to the balloon. If it takes 10 newtons of force to hold a 0.1 Coulomb particle rest in an electric field, the strength of the field there. The electric field strength is the force divided by the magnitude of the charge. You take the force of 10 newtons divided by the 0.1 coulombs, and you end up with 100 newtons per coulomb. And in the electric field surrounding a group of charged particles, field strength is greater where the field's lines are closest together. Electrons on the surface of a conductor will arrange themselves such that the electric field will cancel to zero inside. That's an equal potential surface. The change in potential energy of a charged particle depends upon the work that you do on it. Normally, a rubber balloon is charged to thousands of volts, but it has a relatively small amount of charge, which is why it's okay to touch a charged balloon. A superconductor has the property of having a very low electrical resistance. In other words, it conducts very readily. Be very careful. Look at these. They look alike. Make sure when you read test questions that you differentiate between them. Electric potential energy are none of these. Okay, the electric potential is the electric potential energy per charge. So it's a ratio of energy per charge in units of joules per coulomb. Electric potential energy has the units of joules, and the units will guide you here. Units can be your friend. Voltage is an electric potential energy per charge measure in units of volts, okay, which is 1 volt is 1 joule per coulomb. The thing that we measure in joules per coulomb is voltage. Capacitor can store charge and electrical energy, so capacitor stores both. Thank you.